if there is no external force. Alright, Schmidt-Schlong's still here, and last time we showed you the rotational equivalents of these translational stuff, and you may be wondering what's the rotational equivalent of mass, and that is rotational inertia. I think that's an I. Right? And this signifies how difficult it is to rotate an object, and well, the bigger it is, the more difficult. So for a point mass, this is equal to the summing up of all mr squareds, where m is equal to mass and r is equal to the perpendicular distance to the rotational axis. It's only for a point mass. If you want to do something like a disk or something, then you've got to do this integral thing. Integral of r squared with respect to m. And well, we're not going to go over that. You know, well, you should know, for a disk, it's equal to 1/2 mr squared. If you want a full list on this, you can go ask Ms. Chang or something, I don't know.
More exciting version of Schmidt-Schlong here. As you remember, the translational form of Newton's second law would be written out as F equals ma, and it magically just appeared here, and which means the net force of an object is equal to the mass times its acceleration. But when we talk in terms of rotation, we have this new little letter here, the tau, which it stands for torque, okay? And torque, in terms of rotation, is a spinning or twisting force acting upon an object. And if you remember, m would be I for rotational inertia, and a would be translated into alpha. So we have our net torque is equal to our rotational inertia times angular acceleration. Torque also equals to the net force acting upon an object times the perpendicular radius. So here we go. We got net torque equals force times perpendicular radius. So I'm going to draw a really nice door over here. Okay? We got a little doorknob right here, and we have, what do you call it? Hinges? Yeah, we have hinges right over yonder. Okay? So the radius, leave, and we have the hinges somewhere over yonder. The perpendicular radius would be this length from the door knob to the hinges. And the force that I would apply would be the pulling motion of when I pull the door. When that happens, the hinges will rotate, and the torque force would be the force that I applied while I pull times the radius from the knob to the hinges. When looking at rotation, we must also look at momentum. If you remember in translational motion, momentum is equal to an object's mass times its velocity. When we translate this into rotational terms, we have angular momentum is equal to an object's rotational inertia times its angular velocity. Now, as we remember, momentum is conserved if no external forces are acted upon. In translation, we have Pi is equal to Pf, meaning that the initial momentum is always equal to the final momentum, and it never changes throughout a system. Same thing in regards to angular momentum. We have Li is equal to Lf. Granted that no outside force or torque is given upon the system. So angular momentum, just like translational momentum, is always conserved. I'm Schmidt-Schlong. Now if we segue onto torque and whatnot, we must also note that angular momentum is equal to the integral of our torque in respect to time. So this whole time we've been talking about translation, and we've just gone over rotation. Now welcome to day 3. We're going to put them together. Okay? So let's say we have a circular object and it's translating. Okay? So in translational motion, we have velocities all going forward in the same direction. Okay? Then we have rotation, in which we have one velocity going this way, and then when it turns, we have a negative velocity down here. And then finally, once we put them together, welcome to day 3, we have rolling motion, in which there's no velocity at the bottom. This is 0. At the top, we have 2v, and then somewhere around while it's rotating in the middle, we have v. My name is Hovik Buchin, Dr. Schmidt-Schlong. You've just been schooled.
Hi, Dennis here, and I'm going to push this door. The hinges act as a pivot to cause it to rotate instead of translate.
My name's Alfredo Pasqua, and I will drop this broom.
Dude, that's translation.
Shit!
This is translation.
This is rotation. Now I get it.
Now we can be
Physics gods.
Dennis here with rotational inertia. As you guys might know, rotational inertia is an object's resistance to change upon rotation. Now, I've got these two perfectly cylindrical objects. Got a glue stick and a pen. I'm going to roll them down to see which one has the lower moment of rotational inertia. It's a tie. What does that mean? It means both objects have the same rotational inertia. Their resistance to change in rotation is exactly the same. It's the same. Get over it. Cold, hot, come together. Storm.
Alright, so we can start with the torque problem. See, this question is asking figure right here, shows a uniform disk with a mass 2.5 kilograms and a radius of 20 centimeters mounted on a fixed horizontal axle, and a block with a mass of 1.2 kilograms, this thing, hangs with a massless cord that is wrapped around the rim of the disk. Now we gotta find the acceleration of the block, and the disk, because they share the same acceleration, remember that, and the tension in the cord. The cord doesn't slip and there's no friction, so this problem's pretty easy. We just gotta use Newton's second law. Yeah, okay, let's start. So, we're gonna look at the disk as a system, and we're gonna look at the block as a system. Let's start with the disk. We know that this is mass m right here, and this is a radius, the radius r. We know tension is pulling this way and this way because, you know, Newton's third law. So then we can start doing this using Newton's second law, which is of rotation. So that's equal to torque is equal to rotational inertia times angular acceleration, torque net. And by looking at this, we can see that torque net is equal to negative radius times tension, because perpendicular and stuff. This whole thing is negative because it's going clockwise in respect to everything else. Yeah, I don't know. Anyway, we're going to replace the rotational inertia disk with 1/2 mr squared, because, you know, that's just how it is. And angular acceleration with linear acceleration over radius. And looking at this, we can cancel out r squared with this r and this r, because math. So negative 2 to 1/2 ma. Now let's look at the blockage system. So first let's draw a free body diagram. This is m, as you can see, and then this is gravitational force and tension, as you can see here. And let's use Newton's second law of linear motion. So F is equal to F net. Oops, I wrote net. Equals ma. And now we can sum up the net forces. And that would be T minus mg. Mg is negative because it's pointing the same way as, you know, that's why we made this negative, the torque, and equal to ma. Now we can see we have these two equations. Let's circle them. These two, and we can sum them up. So let's do that over here. So let's just add them, you know, down. Okay, negative mg is equal to 1/2 ma plus, big MA, small ma. Now with math we can take out the a plus m, negative mg, and just divide both sides by this thing. So negative mg over 1/2 m plus m is equal to a. If we plug it all in, and we have all of these because, let's look at that, m is equal to this, big M is equal to that, big R is equal to this, don't forget to turn it into meters, and small m is equal to this, and yeah, those are, and we know g is equal to 9.8. So doing all that, we get a is equal to, let me look at my answer key, yes, is equal to, yes, negative 4.8 meters per second squared. Negative 4.8 meters per second squared. And yeah, that's for finding acceleration. Now the problem is also asking for tension, but that's easy peasy to solve, as we can just look at this equation. And now that we know A, we can just plug it into here. So let's do that right here. Let's just move the negative to the other side for convenience. T is equal to 1/2. M is equal to 2.5, big M, 2.5, and times negative 4.8, and oops, I forgot to move the negative, so let's do that, negative 1. And then we can find that T is equal to 6 newtons. Yeah, that's tension. Nice. So let's not forget the problem is also asking for the angular acceleration, which we know is equal to linear acceleration over radius. And we know from previous problem is that the linear acceleration is negative 4.8. The radius is 20 centimeters, which when converted to meters is equal to 0.2. And because of that, we find that the angular acceleration is equal to with the answer key, negative 24 rad per second squared. Easy. And yeah. So next we'll be moving on to a rotational kinetic energy problem, and we'll be using the same situation as before. So the tension is 6 newtons, the angular acceleration is negative 24 rads per second squared, and we want to find the kinetic energy at t equals 2.5 seconds. See, this problem is pretty simple. So we know that the rotational kinetic energy, K, is equal to 1/2 rotational inertia times angular velocity squared. And we know that the rotational inertia of a disk, as stated before, is 1/2 mr squared. But we don't know what angular velocity is, so we'll just leave it like that. But how do we find it at 2.5 seconds? We just use the constant angular acceleration equation. This one, oops, not that. W is equal to W naught. This angular acceleration times the time. So we want to find that. So equals, it starts at rest, so initial angular velocity is 0 plus angular acceleration, so we know that's negative 24. And time would be at 2.5 seconds. And this means W is equal to, let me see, my answer key, oops, wrong one. Answer key is equal to negative 60 rads per second. And easily plug that in here. So now we have, let me write it right here, it's kind of tiny, 1/2 mr squared times 60 squared. And we know that from the previous problem that r is equal to 0.2 meters. So let me write that. M is equal to 0.2 meters. And we also know that mass is equal to, let's see, mass is equal to 2.5 kilograms. That would be 2.5. You do this all together, you can find the kinetic energy at 2.5 seconds is, let me look at the answer key, 90 joules. Wow. Very good. And there you have it. Another way we can solve this problem is using work. Because we know work is equal to change in kinetic energy. That's Ki. And we know Ki is equal to 0 since it starts at rest. So we can just think of work is equal to Kf, which is what we want to find. And we know for linear work, that's equal to, work is equal to F times D. You think of the rotational analog as work as being equated to torque times angular displacement. Now torque, we know that is equal to R times perpendicular force, and that's equal to, we know that the radius is equal to 0.2, and the force pulling it is equal to 6 newtons, because as stated previously. You know, angular displacement, actually we don't know this, so we gotta use the constant angular acceleration equation. Changing theta is equal to Wit plus 1/2 angular acceleration t squared, and we know Wi is 0 since it starts at rest again, so it's 1/2 negative 24 t 2.5 squared, and that is equal to, what is the displacement? Let me look at that. And that is equal to 75 on this displacement, so rad. So easy, and we just put that over here, so 75. And we find that is also equal to, oops, what am I doing? That is also equal to 90 joules. Wow, same answer as we got before. This time we used work. Wow, rotation's so easy.